Your homework last night was worksheet number 9. We had 7 questions to do. The questions that I want to do here today are questions 3, the first part of 5, 5A, and we'll do number 7 in its entirety. If you struggled with any of the other questions beyond 3, 5A, or 7, then try them again after we've gone over these. I think, because these are 3 pretty representative questions of what we see on this worksheet, I think that if you're able to understand what we do on these 3 questions, you should be able to get the rest of the questions. But let me know if you don't, and I can help you out with that. All right, question number 3 on worksheet number 9 says, an electron is accelerated through a potential difference of 9 volts. The electron begins at a speed of 6.00 times 10 to the 4 meters per second. What is the final speed of the electron? This electron is speeding up. It's accelerating through a potential difference of 9 volts. It's starting at a certain speed. It's speeding up. That's like a car doing what? Up the hill or down the hill? It's like a car going down the hill. So we're going to say EI is equal to EF, of course. But we're going to say that we start off with potential energy. That's what a car starts off with at the top of the hill is potential. It's not QV, it's MGH. But it's still potential energy. Now, if that car is moving at the top of the hill, like this charged particle is when the problem starts, then that car also has kinetic, not just potential. So we're going to say that this charged particle has potential and kinetic energy at the beginning of this problem, like a car at the top of the hill that was moving would have. The final energy, the car gets to the bottom of the hill, what kind of energy does it have? Kinetic energy, right? Now, does it also have potential energy? Well, it's possible. Okay, we don't know for sure in this question if we're actually at the bottom of the hill. We probably are. It says what's the final speed of the electron. But even if we're not, it's okay. Just like that quiz question that we just did, if we assumed that the final potential wasn't 0, that's okay. If we assumed that the final potential was 6, that's fine. Just understand that if the final potential, if we're saying the final potential is 6, then the initial potential wouldn't be 9. The initial potential would be 15, because we're told the potential difference is 9. Does that make sense? So use 9 and 0. That's the easiest thing to do. But if you use 15 and 6, or 24 and 18, it doesn't really matter. 24 and 15, it doesn't really matter because the potential difference in all of those cases is still 9 volts, and that's what we're told in this question. I'm going to assume the final potential is 0 because it's easier mathematically. That makes the initial potential 9 volts. We're talking about an electron, so we'll get the data for that on your data sheet, the mass of it. The initial speed is 6 times 10 to the 4 meters per second. That's a pretty fast speed to start off with. We know that our final answer should be a bigger number than that, right? If it's not, then we know we've made a mistake because we know that this charged particle is speeding up. We know that a car at the bottom of the hill is moving faster than it is at the top of the hill. Somebody yesterday in one of the classes asked me, can we cancel out the mass because it appears in both sides, the left and the right side? The answer is no. Why can't we cancel out the mass here? Even though it is on both sides. It's not in all the terms, right? Solve for VF here. Okay, get this number. Get this number. Then add those 2 numbers up. Then let's multiply it by 2, divide by 9.11, square root. We end up getting a VF of 1.78 times 10 to the 6 meters per second. Does that seem reasonable? Well, it's faster. It's about 100 times faster than the speed of the particle when we started the question. Car speeds up when it goes down the hill. Yeah, it seems reasonable. It's not greater than 3 times 10 to the 8, which is the maximum possible speed that we can get. So it seems perfectly reasonable. It doesn't guarantee that we're correct in the question, but there's a pretty good chance that we are. At least it's not any kind of indication that we're wrong with it. All right, that's question number 3. Let's take a look at question number 5 on worksheet number 9, at least question number 5A. This one says a potential difference of 100 volts exists between two parallel plates that are this far apart. So the potential difference is 100 volts. We're going to say the initial potential, if we're analyzing the entire problem from start to finish, we're going to say the initial potential is 100, the final potential is 0. But we could say the initial potential was 160 and the final potential was 60. It doesn't really matter, right? As long as the potential difference is 100 volts. Now, first part of the question says the electron begins at rest at one of the plates and accelerates toward the second plate. How fast is the electron moving when it's traveled 4 centimeters, when it's traveled a quarter of the way across? Charged particles speeding up. So we're going to say, again, EI equals EF. It's like a car going down the hill. It's a conversion of potential energy. Starts at rest, so there is no kinetic energy at the top of the hill. A conversion of potential energy to kinetic energy. Now, you got a couple of options here. Some people will say that there is a potential energy at the end of this. And they'll say that because, oh, we haven't traveled all the way across. We know we've only traveled a quarter of the way across. Some people will say, well, I want to define that as 0. I want to say that's 0 potential. You can do either way. We'll take a look at both ways. Okay, let's assume first that there is a potential at the end of this problem, the end of problem A, when it's gone 4 centimeters. If we do, then we're going to solve it like this. 1.6 times 10 to the minus 19 times our initial potential, which is 100. My final potential, in this case, would be 75. Why would it be 75? Well, if the distance between the plates is 16 centimeters, and I've gone 4 centimeters across, then I've only gone a quarter of the way across. I've only gone through a quarter of the potential difference. So if we're starting at 100, then I'm still at 75. Does that make sense? Other than that, those distances involved are irrelevant. We only need that 16 and that 4 centimeters to remind us that, look, it's only going a quarter of the way across. Therefore, the entire potential difference that I started with 100 volts isn't the entire potential difference in this question. We're only going through a potential difference of 25. When you solve for VF there, it works out to be 2.96 times 10 to the 6. You're going to calculate the number on the left, calculate this number right here, take it over to the other side by subtracting, then multiply by 2, divide by 9.11, and then square root. What if we had chosen to do it a little bit differently? What if we had said QVI is equal to 1F MVF squared? What if we had said, look, I don't like this whole VF is equal to 75 thing. I'm only gone a quarter of the way through, I understand that, but I like seeing VF is equal to 0. You can do that. You can always do that. But if you do that, then we're not going to say the initial potential is 100. Relative to the end, the initial potential would be what? 25. The bottom line is, if I've only gone a quarter of the way through, then the potential difference that I go through must be 25 volts. Whether I consider it to be 175 or 25 and 0 makes no difference. The difference between the two has to be 25 volts. When you do this, solve for VF, it's going to work out to be 2.96 times 10 to the 6. It's the exact same thing. Now, mathematically, the one in green here is probably a little bit easier. I don't know which way is easier for you to understand. Most times, I think it's easier to understand when we say VF is equal to 0. In this case, maybe not, because you can clearly see that we're not all the way across. Doesn't matter. Okay, whatever you find easier. Question B would work the same way, except obviously the difference in the potential between the end and the beginning would be 50 volts. Question C, well, we've gone all the way across, so it makes sense in question C that we make VF equal to 0 and VI equal to 100 in that case. Does that make sense? All right, finally, we want to try question 7. There's 2 parts to 7, 7A, 7B. Both of them start off the same way. An electron enters the gap between parallel plates with a potential difference of 20 volts, 10 centimeters apart, at 6.0 times 10 to the 6 meters per second. How fast is the electron moving when it reaches the second plate if it's moving from the negative to the positive, if it's moving from the positive to the negative? So question 6a, we've got a positive plate, we've got a negative plate, we've got a negative particle, an electron, in question 7a moving from the negative to the positive. It starts off with a certain speed here, 6.00 times 10 to the 6 meters per second. What's going to happen to this electron? Is it going to speed up or is it going to slow down as it goes through this electric field between these plates? Tell me, is it going to speed up or slow down? What is it? It's going to speed up. Why? It's attracted to the positive. It's repelled by the negative. So we're going to do the whole EI equals EF thing. We're going to do that in question B as well. But the way we set that up is going to be slightly different. This is a car going down the hill. At the top of the hill, we have potential energy, MGH, or in this case, QVI. Now, if the car is moving at the top of the hill at the very beginning, then it's also got kinetic energy. Keep these two straight, right? This is initial potential. This is initial speed. Two completely different things. EF, well, when it reaches the other plate, we're going to say that it has only kinetic energy. You could say that it has potential as well if you wanted to. But the potential difference, the difference between the initial and the final, any way you look at it, would have to be 20 volts. Whether you go with 20 and 0, which is what I'm going to do, or whether you go with 37 and 17, it doesn't really matter as long as the difference is 20. Okay, we plug in our numbers here. And we end up solving for VF. VF in question A works out to be 6.56 times 10 to the 6 meters per second. The initial speed was 6 times 10 to the 6. Now we're at 6.56. We've sped up. Seems like a reasonable number. It's slower than the speed of light. It's faster than we started, so it seems pretty reasonable. Question B. This is the one, Rob, that's a lot like question number 6, where we're slowing down. How are we slowing down in question B? Well, we've got a positive plate and we've got a negative plate still. But this time we've got a negative particle leaving the positive plate with an initial speed of 6 times 10 to the 6. This charged particle is going to slow down because it's repelled by the negative. It's pushed away by the negative. It's pulled back toward the positive. It's going to slow down just like a car is being pulled back to the bottom of the hill as it's going up the hill. If it's slowing down, we're going to say that it starts off with kinetic energy. And it ends up with, when it reaches the other side, car going up the hill has potential energy. Right? Kinetic converted to potential. Kinetic decreases, potential increases. But we'll assume that we also have a final speed. It's also moving at the end of it. Let's plug in our numbers for this. When we do, we end up getting a final speed here of 5.38 times 10 to the 6 meters per second. A little bit slower than what we started with. Should it be? Yeah. Yeah, it should be. It's slowing down. We established why it was slowing down. So the number you're going to get is going to be smaller than the number that we started with, 6 times 10 to the 8. 6 times 10 to the 6, I should say. Does that make sense? So number 6, Rob, is going to be pretty much the same as that, right? Except you don't have to go through that process of figuring out that it's slowing down, because you're told in question 6 that it's slowing down. Here we had to figure that out. We're good with those questions? Yep. Question 7b, why do you have to assume that it still have kinetic energy? Well, the reason is because in question 7b, we're asked for the speed of the electron when it reaches the other plate. Now, we'll assume that it is still moving when it reaches the other plate, because we're asked to solve for a speed. If we solve for the speed and it works out to be 0, then, okay, we assumed wrong. But even if we make that assumption, we'll find that the final speed is 0. So it's not an assumption that's going to cause us to do something wrong, right? Solve for the final speed, 0. Oh, we're wrong. It's not moving when it reaches the other plate, but we've still got the answer that we're looking for. Let's spend a few minutes reviewing for our test tomorrow. Topic number 1, there's 9 of them here that I've identified for tomorrow's test. First one is charge. What kind of charges do we have? Okay, positive and negative. Where do they come from? Okay, do you have more protons or more electrons? The units for charge? What's the units for charge? Coulombs. Remember that we don't often see those units, though. We often see something like microcoulombs or millicoulombs. Every once in a while, we might see a nanocoulomb or something we've never seen before in our lives. Okay, just be prepared to do that conversion. Okay, the conversion factor is always on your data sheet, so you never have to worry about remembering that a micro is 10 to the minus 6 or whatever. Don't memorize the charge of the alpha particle, the electron, the proton. Just know where to find it. Okay, on your data sheet, it'll say the charge of an alpha particle is plus 2e. Remember that that amounts to 2 times the elementary charge, 1.6 times 10 to the minus 19, or 3.2 times 10 to the minus 19. One thing that we've done a few times, and that we will have to do again, whether it's on tomorrow's test or whether it's on an exam, a diploma exam, you'll have to do this again. Find the number of the electrons. When we're trying to find a number of something, remember we always take the total something and divide it by that something for 1. The total energy divided by the energy of 1. The total momentum, the momentum for 1. The total charge divided by the charge for 1. Usually when you're looking for a number of electrons, it's going to be the total charge divided by the charge for 1 electron. So whatever number you have, however many coulombs you have, divided by 1.6 times 10 to the minus 19. That's going to give you a number of electrons. Second bullet, there's not a whole lot with this, conductors and insulators. We just have to remember what the difference is between the two, and we have to remember some examples. You don't need to tell me whether gold is a better conductor than copper, or copper is better than gold. Just remember that generally metals are good conductors. You don't need to remember whether glass is a better insulator than wood, or wood is a better insulator than glass. You just need to remember that non-metals are usually insulators. Okay, things like generalities like that for bullet number 2 there. Number 3, we talk about those 3 laws of electric charge, right, plus the law of conservation of charge. Said a few minutes ago, don't memorize these. You got to know them. Of course, you got to remember them, but you got to be able to apply them as well, and that's the big thing here. And we gave you a couple of examples as we were going through this for the first time in the notes. Just going to refresh your memory on these, not because you're going to see either of these on tomorrow's test. In all likelihood, you will not. But the thought process that you go through in interpreting these examples is the exact same thought process you go through on your test tomorrow and on your diploma exam coming up in June. This was an electrostatic precipitator, okay, an air filter basically. You got this air with dust particles that you want to filter out. So what happens? These neutral dust particles touch this positively charged blue rod here. Sorry, this negatively charged blue rod. What happens to these neutral dust particles as they touch this negatively charged blue rod? They become charged. What's the charge they gain? They become negative, right? Why do they become negative? Well, when neutral touches negative, what happens? They want to balance out. That's the law of conservation of charge. So there's the application that we're looking for. Not just a matter of remembering that the conservation of charge says that it can't be created or destroyed, but rather applying it so that when we have dust particles in the air touching a positively charged rod, or a negatively charged rod, they become negative. What happens when those negatively charged dust particles go through these positively charged plates? They stick to it. They get attracted, right? It's that first law of electric charge. Charged objects attract neutral objects. Charged objects, positive charge attracts negative charge. Opposites attract, right? So we're applying the law of conservation of charge and the fact that opposites attract all within this thing that a month ago you'd never seen before. We can apply that. We can do that. We see something like this that we've never seen before. We can interpret that. It's usually not that hard if we're not afraid to just give it a little bit of thought. This is the other example that we did in class when we went through this for the first time. We had this paint gun that's electrostatically charged, charges the paint droplets, which causes very little wastage, remember, of the paint, right? It sticks to the metal and stays there. We have this positively charged rod in this paint gun. What happens is these paint particles go through this paint gun and they touch this positively charged rod. What happens to the paint? It becomes positive, right? Neutral touches positive. They want to balance out, so they become positive and positive. Again, the law of conservation of charge. Those positively charged paint bubbles, when they go to this grounded fence, they stick to it because positive is attracted to neutral, right? This neutral fence. And more the metal fence than it would be the ground, of course, because the metal fence is metal. It's a good conductor. So we've got charged objects attracted to neutral objects here now. Conservation of charge, charged objects attracted to neutral objects. So we've got four little things here, the three laws plus conservation of charge. We've just addressed first one, the third one, and the law of conservation of charge with these two examples here. That's what you're going to see, is that type of thing, as opposed to recite the three laws of electric charge. Okay? We can charge objects in two ways, conduction and induction. And you're going to have to know about that. You sometimes see questions that are pretty straightforward with this whole charging thing, but we also sometimes see applications like what you see up on the board here right now, this whole idea of lightning. Let's assume that lightning isn't striking yet. We've got a negatively charged cloud right here, and we've got a neutral Earth down here. What happens to the positive charges on that Earth? They stay where they are. What happens to the negatives? They repel. They get pushed away. So these negatives are going to be down here. What we've just done is created a temporary separation of charge on the Earth. The Earth is now positive near the top, and it's negative somewhere down below. Okay, the diagram that we drew in class the day that we did this was, here's a neutral object. Bring a negatively charged object nearby. What happens? We push away these negatives, and we create a temporary separation of charge in this neutral object. Isn't this the exact same thing as what we drew right here? Of course it is, right? Be able to apply that picture that we drew in class to a new situation like before lightning strikes. Now, what's going to happen when lightning strikes? That was charging by induction. What's going to happen when the lightning is actually striking? You get a neutral Earth. You got a negatively charged cloud up here. At least that side is negative. Electrons are going to go down here. Charge on the tree and the charge on the Earth nearest the cloud is going to become non-neutral. It's going to become negative, right? Because you've just transferred electrons down to the tree and down to the ground. What's that? Charging by what? That's charging by conduction, because you're transferring charges, physically transferring charges. Remember that even with induction, sometimes you have electrons moving, right? That's conduction. But we still call the process of charging this object, and for that matter, charging the Earth, because it becomes charged as the negatives go down into the Earth. We still not call that induction, because the object doing the charging, the thing that's causing it, isn't touching and it's not transferring charge. This is conduction, because the object doing the charging is transferring charge downward. So the difference between conduction and induction, and again some applications of the two. We talked about Coulomb's law, and we talked about Coulomb's torsion balance experiment. The torsion balance experiment, remember we had these charges that we brought near each other. They repelled or attracted. We observed how much the string twists. That gives us the force. Coulomb would have done 3 sets of experiments here in order to derive this law. In the first experiment, he would have manipulated the first charge. Responding to that would have been the force. He would have kept the second charge, and he would have kept the distance separating the charges constant. When he plotted that graph of that data, he got a straight line. The second set of experiments he would have performed, he would have changed the value of Q2. F would have responded to that. What would my control variables be in that case? Q1 and R. Plot that graph, straight line. Finally, he would have manipulated the value of R, responding force. What would he have kept constant? Q1 and Q2. What shape is that going to be? Goes down, right? As R goes up, F goes down. That tells him that F is inversely related to the square of the distance. Puts these together, ends up with a constant times Q1, Q2 over R squared. That is Coulomb's law. Now we got to be able to apply Coulomb's law. Simply two charges, find the force between them, find the acceleration by using that, and F equals ma. We got to be able to find the force on the middle one, say, due to the other two. We also have to be able to find the force on the middle one due to the other two when it's a two-dimensional problem. It's probably a pretty good chance you're going to get one of these. Probably a pretty good chance you're going to get one of these on tomorrow's test. It's this whole variable value changing thing. Why do I throw that in there? Well, I can throw that in there anytime we have an equation. Any equation. We did it with momentum. We did it with impulse. We can do it with Coulomb's law. Let's say the original force is F, and it's equal to KQ1, Q2 over R squared. Let's say we double both of the charges. So my new force is K times 2Q1 times 2Q2. Let's say we're cutting the distance separating them in half. So now it's not R, now it's going to be 1/2 R. Don't forget to square the entire distance, which is half R. Pull the 2 and the 2 out front, it becomes 4. Pull the half squared out front, it becomes 1/2 squared is 1/4. 4 over 1/4 is 16. So if you double both charges, cut in half the distance that separates the two charges, the new force is going to be 16 times whatever the old force is. Okay, we can do that with this equation, with electric fields, with momentum, with any equation that we're going to learn next unit. Doesn't matter. Be prepared for that. Be prepared for that on tomorrow's test. We talked about electric fields. Okay. This is a big one right here, the effect on a positive charge on a negative charge. Here's a field to the right. Positive is going to be pushed to the right. Negative is going to be pushed which way? To the left, opposite to the direction of the field. My equations. Okay, 3 equations, producer, experiencer, parallel plate equation, VVC, variable value changing again with any of those equations. Here's 2 charges. What's the net electric field midway between those charges, or 10 centimeters to the right of the second charge? Charge distribution. Basically, what you need to know about this is you got a bunch of extra electrons on this conductor. Where do they go? They always go where? To the outer surface. If it's a uniform surface, then they're going to be evenly distributed. If it's a pointy surface, then they're going to collect more at the point. They're going to be more concentrated at the point than they are everywhere else. What about the electric field in the conductor, inside the conductor? It's going to be 0. There is no electric field inside the conductor. That's why it's safe to be inside a car in a lightning storm. These terms we talked about, right? Be able to do this conversion. Electron volts to joules, joules to electron volts. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. If we're trying to find electron volts from joules, then we're going to do this. If we're trying to find the number of joules given the number of electron volts, then we're going to put our x on the bottom and solve for x. And finally, number 9, our last topic that we've been looking at over the last couple of days, this is just conservation of energy. Every time you see a charged particle speeding up or slowing down, do conservation of energy. Car going up the hill, car going down the hill. Hey, we did this question yesterday, I think it was. It looks really hard, but in the end, what does it involve? It involves kinetic energy. It involves charged particles speeding up. Okay, be able to, once again, not just do the straightforward questions, although that's important, be able to apply it in new situations. All right, there are 3 questions that I'd like to take a look at here over the last 10 minutes or so. We've done a number of multiple choice questions as this unit has progressed, and as the last unit, for that matter, has progressed as well. We're going to do 3 more here today. The rest of them I'll leave you with yourself. I strongly suggest that you do every single one of those as practice for tomorrow's test. You will not likely see any of them on the test, but it's good practice whether you see those questions directly or not, because it gets you into the right frame of mind. This is the kind of thing that's asked, even if it's not the exact question. 61, 62, and 63 all involve this picture, this diagram that you see up on the board. A Van de Graaff generator that is negatively charged, this neutral pith ball that is attracted towards it, because charged objects attract neutral objects. And we're asked to find 3 things. Why it's attracted to the neutral object, which is the direction of the force, and finally, the really tough one, the magnitude of the force. I'm going to give you about 4 minutes to see what you can do with these 3 questions. You'll probably struggle a little bit with question 63. That's okay. In 4 minutes, we'll take a look at all 3 of these. Well, let's take a look at this, okay? Just so that we don't run out of time here at the end. 61 says, when the neutral pith ball is placed near the Van de Graaff generator, the pith ball is attracted to the generator because of what? We don't even need to see the picture to know the answer to this question. How many people said A? B? C? D? Okay, the answer is A, yes. It's charging by induction. When a charged object is brought near a neutral object, there's a separation of charge, a temporary separation of charge induced, induction, in that neutral object. That temporary separation of charge causes the side that's closest to the charging object to be opposite, so they attract. It attracts because of that temporary separation of charge. It attracts because of induction. Question 62, the direction of the electric force on the pith ball. See where you see the diagram there, the negative Van de Graaff, you see the pith ball being attracted towards it. How many people said A for this one, 62? B? C? D? Good, the answer is B. How do we know that? This one's pretty straightforward, right? If it's attracted to the left, then the force of attraction must be to the left. Now, the last question, that's the challenging one here. And it really is a challenging question. We want to find the electric force. Now, the temptation when we want to find the electric force is to use this equation. And I'm not going to lie to you, that's exactly what I wanted to do the first time I saw this question. Then I realized, well, A, I don't know what the charge of the Van de Graaff generator is. B, the pith ball doesn't even have a charge. So I couldn't find any way to make that equation work. Then my next thought, myself, was, all right, I know the electric field experiencer equation has force in it. Okay, let's say Q times the electric field. Well, I don't know what charge is, and I don't know what the electric field strength is. So that doesn't seem to work for me. So then, honestly, I was at a little bit of a loss for a little while. Here's what happens when I'm at a loss. I start just doing things that are valid that may not lead me anywhere. What I started doing is just drawing a picture. I thought, okay, I don't know what to do here. Let's draw a picture. Let's draw the forces acting on this pith ball and see if something comes out of that. We know the electric force is to the left. We know that because it's attracted to the left, right? We solved for that in question 62. We also know there's a force of gravity acting downwards on this pith ball. And we know that there's a force of the string or we'll call it Ft for the tension acting upwards at an angle. When I drew that, that's when it struck me. And there's 100% honest here, guys. When I drew this, I didn't know exactly why I was drawing that. I didn't know where I was going with this question as I was drawing the free body diagram for the first time. It wasn't until I had the diagram drawn that it all of a sudden popped out of the page at me here. Okay. I looked at this and said, at this point, it struck me that, look, the net force acting on this pith ball is 0. Otherwise, it wouldn't sit there. It would move if the net force wasn't 0, right? If there was a force that supplied an unbalanced force. The net force is 0. That must mean the force to the left, the electric force, is balanced by a force to the right. And the force downward is balanced by a force upward. Does that make sense? This force has to balance this one. This force has to balance this one. Otherwise, this charge isn't going to just sit there. It's going to move one way or the other. Well, I can find the force of gravity easily. It's 2.5 times 10 to the negative 4 times 9.81. That gives me 0.00245 newtons. Well, if the force of gravity down is 0.00245, then this force is also 0.00245 newtons. And if that's 0.00245, then I can find this force by saying tan 20 degrees is equal to opposite over adjacent. We solve for the value of x there. That x is actually the x component of the tension in the string, but we know that it has to balance the electric force. So whatever we just solve for is also the value of the electric force. That's a tough question. That's a really tough question. Okay, you see that having never seen something like that before on an exam, and it's not going to go that well. It wouldn't, honestly, I bet if you take 100 Physics 30 teachers, give them a limited, very, very short amount of time, say 2 minutes to answer that question, I bet there's at least 50 that don't get that question. Now, we've seen something like that. The first time this appeared on the exam, I didn't think it was that fair. I thought it was too tough. But something like this has appeared 4 or 5 times since that. I think it was fair, the 4 or 5 times since that, because students can be exposed to it. So you don't have to think quite as hard about it now, right? You still have to think, but at least you have somewhere to start. Listen, KQ1, Q2 over R squared doesn't work for you. E is equal to F over Q doesn't work for you. Try something else, like a free body diagram. Do some trigonometry, do some geometry, and hey, maybe you get lucky and something works out for you. Does that make sense now? All right. That's all I have for today.